Math 2414, review, trig identities, Pythagorean identities and their variations. While teaching the section on trig integrals, a few students asked if I could put together a video or a series of videos reviewing some trigonometric identities. Of course I can, but I'm going to be going through these kind of faster than as if I were teaching them from scratch from a trigonometry perspective, because you're in calculus too, and I shouldn't have to teach trigonometry from the beginning. So this is more of a review than an introduction. But I can't help myself. I'll be deriving pretty much everything. All right, so what do I mean by Pythagorean identities and their variations? Well, Pythagorean identities, as the name implies, are stem from the Pythagorean Theorem. So just a quick review, as if you don't know the Pythagorean Theorem already. Pythagorean Theorem says if you have a right triangle and you label 3 of the sides, then the sum of the squares of the legs is equal to the square of the hypotenuse. Now you might be thinking, I thought it was a squared plus b squared equals c squared. Well, yeah, that's right if you label your triangle correctly, but if I make this side a and this side c, then a squared plus b squared plus c squared is flat out wrong. I personally do not like saying a squared plus b squared equals c squared. Those names are so arbitrary and have no meaning unless you have a picture associated with them. I prefer to refer to the sides of a triangle relative to something specific instead of just arbitrary names. And since we're discussing trigonometry and the Pythagorean Theorem, what better way to refer to the sides of a triangle than in reference to an angle? So let's put an angle here and we'll call it theta. We can call it x, we can call it whatever we want, but we'll just be typical and call it theta. And relative to theta, we can say that this bottom side is the adjacent side, so we'll put ADJ for adjacent. Opposite side is, well, the opposite side, so we'll abbreviate it OPP. Insert your own naughty by nature joke there. And the hypotenuse we'll label HYP. So if we get the Pythagorean Theorem on this, it would be, let's start with opposite. Opposite squared plus adjacent squared is equal to hypotenuse squared. So that's the Pythagorean Theorem in terms of opposite, adjacent, and hypotenuse, which means we're focusing on a specific angle in the right triangle. So what does this have to do with trigonometry? Well, as of right now, not much. Aside from labeling the sides opposite and adjacent, there's not much trig to this. But trigonometry is all about ratios of sides in a right triangle. For example, sine of theta is opposite over hypotenuse, something that you should already know. Cosine of theta is adjacent over a hypotenuse, again, something that you should already know. Tangent of theta is equal to opposite over adjacent, which again is something that you should already know. Of course, there are also the reciprocals of these, the reciprocal of sine being cosecant. So if we quickly listed those, we could say, well, I want to put it next to sine, but I don't have room. So I'm going to move this triangle over just a second. Actually, we don't need the triangle anymore. Cosecant of theta being the reciprocal of sine is hypotenuse over opposite. Secant of theta being the reciprocal of cosine is hypotenuse over adjacent. And cotangent of theta being the reciprocal of tangent is adjacent over opposite. So these are things that you already know. So how can we get these ratios to show up in the Pythagorean Theorem when there are no fractions at all? Make some. To get Pythagorean identities from the Pythagorean Theorem, you just pick one of these 3 expressions and divide both sides by it. For example, let's say that we divide by hypotenuse squared. In other words, we divide everything in this equation by the square of the hypotenuse. Now, this is assuming it's not equal to 0, otherwise the division would be undefined. If we divide everything by the square of the hypotenuse, then this becomes 1. Well, what do we get here? What we would get here is opposite squared over hypotenuse squared. And on the other side of the addition sign, we would get adjacent squared over hypotenuse squared, which almost look like the ratios for sine and cosine, except those ratios have no squares on them. But we can use an exponent rule that says If both sides of a fraction is squared, then you can just square the whole fraction collectively and rewrite the first fraction as the squares of opposite over hypotenuse, and the second one as the squares of adjacent over hypotenuse. Well, opposite over hypotenuse is sine of theta, so we could write this as sine squared theta. Similarly, adjacent over hypotenuse is the cosine of theta, so we could write this as cosine squared theta equals 1. And just like that, we have probably the most common Pythagorean identity in trigonometry, sine squared theta plus cosine squared equals theta equals 1. Because it's addition, it's commutative, we could say cosine squared plus sine squared. And of course, the angle is immaterial as long as the argument of this trig function matches that one. So this could be thetas, these could be x's, these could be 9w's. It doesn't really matter. As long as they match, then the sum of their squares is going to be equal to 1. Let's put that over here. Sine squared theta plus cosine squared theta is equal to 1. All right, so this is one of the big ones, but it does come in a few variations. And what I mean by variations is just this equation, this identity with pieces moved around, terms moved around. For example, if we, let's not make that, I was going to make a list and that was a bar separating it, but it would look like a fraction bar. So let's not do that. Or rather, just right below there, let's write variations of this Pythagorean identity. For example, if I subtract cosine squared from both sides, I would get sine squared theta is equal to 1 minus cosine squared theta. What that basically means is I can replace one with the other. For example, if I ever see a sine squared theta, I can replace it with 1 minus cosine squared theta. Or, if I ever see a 1 minus cosine squared theta, I can replace it with sine squared theta. Or, if we went back to the original version of this and subtracted sine squared from both sides, we would get cosine squared theta equals 1 minus sine squared theta. Those are the three main variations of this Pythagorean identity. It's just a matter of what you're isolating. You want to isolate the constant, isolate the sine squared, isolate the cosine squared. In a lot of things that we're going to do, we are going to be taking advantage of these two versions of this Pythagorean identity, where we have 1 minus cosine squared and replace it with sine squared, or vice versa. Or 1 minus sine squared and replace it with cosine squared, or vice versa. But that's what you would get if you divided this Pythagorean theorem applied to a triangle from a trigonometric perspective and divided everything in that by the square of the hypotenuse. But what if we decided to divide by something different? For example, what if we decided to divide everything by the square of the adjacent side? Now, I'm not going to reinvent the wheel totally, but we will talk it and just write the results. If we took opposite squared plus adjacent squared and divided it by if we took opposite squared plus adjacent squared equals hypotenuse squared and divided all three terms by the adjacent side squared, what would we get? Well, adjacent side squared divided by itself will give us 1. By the way, this is assuming that the adjacent side is not 0, which in right triangle trigonometry isn't a thing, but in circle trig is. On the first term, we would get the square of opposite over adjacent, but that's just the definition of tangent. So we would get tangent squared theta. And on the right side of the equal sign, we would get the square of hypotenuse over adjacent, but that's the definition of secant. And there's our second main Pythagorean identity, tangent squared theta plus 1 equals secant squared theta. And just like this one, it comes in three varieties, depending upon which term you want to isolate. Right now, the secant squared term is isolated. If we isolated the tangent squared term by subtracting 1 from both sides, we would get tangent squared of theta equals secant squared theta minus 1. Or if we were to isolate this 1 by subtracting tangent squared from both sides, we would get 1 equals tangent squared theta minus secant squared theta. Again, all of the Pythagorean identities pretty much come in three variations, depending upon which of its three terms you want to isolate. If we play the same game, but this time divided by the square of the opposite, because it's the only one we haven't talked about yet, we would get yet another Pythagorean identity. But let's just talk it out. If we divide this Pythagorean theorem by the square of the opposite, the first term would become 1, plus, then we would get the square of adjacent over hypotenuse, but that's just the definition of cotangent. I pointed at the wrong one. So 1 plus cotangent squared theta equals, and if we divided hypotenuse squared by opposite squared, it would be the square of, where is it? The square of cosecant. So our third Pythagorean identity is 1 plus cotangent squared theta equals cosecant squared theta. Of course, addition being commutative, I could write this as cotangent squared theta plus 1. And just like the two above it, this comes in 3 variations, depending upon which term you want to isolate. Right now, the cosecant squared is isolated. If I isolated cotangent squared, I would have cotangent squared theta equals cosecant squared theta minus 1. But if I isolated the 1, I would have 1 equals cosecant squared theta minus cotangent squared theta. I'll be honest with you, I would just remember the big 3. Well, the 3 that we get by taking the Pythagorean theorem and dividing by one of its terms throughout. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. 1 plus cotangent squared equals cosecant squared. As long as you know those 3, you're okay. And it's not really that hard to remember. This one's pretty standard. Everybody should just know this instantly. Tangent squared plus 1 equals secant squared. It's not that hard to remember, but assuming that you do, you can get the third one by simply taking the co-functions here. Tangent squared plus 1 equals secant squared. Cotangent squared plus 1 equals cosecant squared. So that's the way I used to remember it. I used to just remember these two, and then I would get the third one by sticking co on each of these trig functions. Alright, so I think that's pretty much all I wanted to say about Pythagorean identities. As we go through some trig integrals, which is what this is leading up to, I may point out another little nifty trick involving this difference here, or any of these differences, because all of these differences are differences of squares and hence factor from an algebra perspective. That can be advantageous in various situations.